You hear lots of folks talking about cam failures, and they failed because the cam wasn't hardened deep enough or wasn't hardened at all. But I don't know that anybody really knows what that looks like. So today I'm going to show you some examples of what actual hardening looks like when it's applied to a camshaft. So lots to talk about today. So again, this one's going to get spicy. So before we get started, I just wanted to let you know I am not a metallurgical expert. I don't have the understanding of the materials and the components and all the different compounds that go into them and all the little details of it. But we will have one on the channel here pretty soon. I'm going to be interviewing Billy Godbold, and a lot of you have probably heard his name before on the Engine Masters program. There's thousands of articles written by Billy. He's got a new book coming out, and that's what I'll be interviewing him for, is his new book release. But Billy is the premier camshaft and lobe designer out there, and there's nobody in the market that knows how these go together, the correct way to make power, and what different components and materials work together and how they work together. And I'm really eager to have him on the channel here hopefully in a month or so. So if you have any questions before you get too far into this video, or you want to come back to this video and leave questions that you have about anything camshaft related, leave them down in the comments, and I'll be sure to add that to our discussion when we talk to Billy. Now, back in part one of the series, we talked about why the reasons a camshaft failed and went over all the details of lifters and springs and why folks totally screw up the pressure on break-in oils and mixing them, playing chemist on your own, all those little details. But one of the recurring comments that I got in that video and have seen in quite a few others is folks will talk about, well, the camshaft wasn't hardened enough, or it didn't have good hardening on it, it was soft. And I'm going to show you what all that looks like today, because I think it's really important to understand what that actually looks like and a little bit of how that process goes. Now, again, I'm no expert in this, and Billy's going to cover it far more in depth, I think, than I am. I think it's one of the topics that we'll talk about, because certainly it's a hot topic. But today I just want to show you some of the little pieces and parts of this, how it goes together, talk about the process, and then I'll show you how you can kind of test this at home with a little bit with a hand tool that's fairly inexpensive to get a hold of. So first of all, I want to talk about the hardening process itself. So we'd made mention of there's a couple of OE core suppliers in the U.S. that are still making cast cam cores, and they're both located in Michigan, and they both cast these the exact same way. Now, most of these are a sand cast type of deal. The metal's poured into there, and then they will finish the journals, and then the lobes are what we call a UGL, an unground lobe. It doesn't have the specs on it. Now, it's within a certain range, because a manufacturer like Comp or Howard's or whoever that's buying this cam is going to want to be able to grind it to whatever spec that they're looking for, and it's typically duration. Lift is obviously very key. Depending on what the engine is, the base circle size is going to change quite dramatically, or could. You may, elect to cut a smaller base circle on it. Those are all important things, and the core supplier needs to know that so they can create you the core that fits into those parameters. Now, again, when it's done from that OE supplier, this is already hardened. They take all of the hardening and do it all right there. Just the final grind is done at it with that grinder. Again, there's a lot of manufacturers out there that are still grinding cams in the US, and once they get that unground camshaft lobe to them or core to them, they will finish off the final core. They'll do their final QC on it, verify it, measure it, and send it out to the customer. Now, the heat treating process is pretty interesting. Most of these are either an induction or a flamed hardened. It don't really matter how it gets done at this point, but it's heated to a very high temperature, and 1700 degrees. I'm not exactly sure there. Again, it's a question that we'll confirm with Billy, but before, when that cam core is ready to be hardened, typically they have a HRC on the hardware, the Rockwell scale, of about 34, 36, I believe is the general range that those cams are. Once they are done and heat treated, and in this condition here where it's, this one's a ground camshaft, but once it's done and ready to go to that supplier to be ground, typically they have the HRC level around 48 to 55. That's generally the range. Now, if you have a hardness of around 50 on the surface, it's typically will let that cam supplier know that the depth of the heat treat has gone deep enough in it that they can grind what they need to grind on it. If that's less than that, if it's a 45, that means that the heat treat may have not got deep enough in there. Now, I can't speak for every camshaft manufacturer out there, but I can tell you that at least with the number of failures that they have to be able to Rockwell test that before they even start doing anything. So if they order 100 of these camshafts, the first one that comes out of the bin is probably going to get tested or it's going to get cut apart. I'll show you that here in just a minute, to verify the depth of the heat treat. That way they know that the other 99 that they're going to grind are going to be at the heat treat depth that they need. But again, we're not going to get really in depth with the process side of things because it doesn't really matter at this point, but I wanted to show you or talk quickly about how that process went, a little bit how that happens. Now, one thing about cast iron cam cores, we'll talk about billet here in a minute too, but even with that Rockwell hardness of 50 to 55, whatever it finishes out to be, cast cam cores are very, very brittle. I see that complaint a lot that they bought a cam from whoever, it was a cast cam, flat tappet cam core or cam, it was sent to them and it was broken. Well, why the hell did they send me a broken camshaft? They didn't. It's that these are extremely brittle. The hardness is good for the pressures it's going to take from the push rod and the lifter and all the pressure that's put on there. But when you talk about actual hardness, through hardness of that camshaft, it's not very hard at all. And unfortunately, I'm going to show you what that looks like here now too. Well, forgive me for this. Now, that's unfortunately what happens. That is a very, very brittle camshaft. It's not hardened ground or hardened all the way through. Now, a tool steel camshaft is different. They through hard those all the way through. So that's why when you hear folks talk about a tool steel camshaft, you can grind those unlimitedly down till they're a nub and there's nothing left to grind on it because the heat treat depth goes all the way through the camshaft. When you talk about a cast cam core, gosh, I feel sorry about that. It's not that way at all. It is not through hardened. They are extremely brittle. And you see that quite frequently, again, with folks complaining that they got a broken camshaft and they just assume that the manufacturer sent it out that way. And that was dropped from, I think of a height of about 3 feet here. And God only knows how FedEx and UPS treat these things. So it's certainly not going to get treated very well. That's why cam manufacturers are usually fairly picky about how they pack them, in a fairly heavy box and bagged and, keep them from sliding around in there. They'll put them in tubes, whatever it takes to keep these cast cam cores together. But unfortunately, that's the catastrophic side of what happens to these cores. Again, it's because it's the material. It's not because the camshaft wasn't hardened. We could harden this one extremely deep and maybe in a 60 as on an HRC scale, and it would still do that. As soon as that thing hits at the right angle, snaps. So it's just the nature of the beast. Now let's talk about hardening and these camshafts. Now, this was a used camshaft. It failed, and what I did is I had it cut down so we could look and see at the heat treating depth in it. You look and see that lobe there, it is clearly worn off. It's got one hell of a taper to it. I think that's a little excessive, but the point is even in a camshaft that failed, we can still look to see how deep the heat treating was, and that's what I want to show you today. So we take a look at this cam that I had cut down. You can see fairly effectively where those lines are on the material and how deep that heat treating goes. If you look here, it's snapped right off at the journal, but you look and see the lines here, you can see just how deep that heat treating goes. And on a cast cam core, they do go fairly deep. We're going to look at a billet one here in just a moment, and it's generally a little less, but that's probably 250 thousandths. That's probably 100 thousandths, somewhere in there. This is the top of the cam, so that's the nose. That's the bottom of the cam, that's the heel. But there's a lot of heat treating in there still. And if you look at it and see how that kind of looks, it's not even. They don't get heat treated through there evenly. It's not a exact process that goes through there. The material may take it a little bit differently, accept the heat a little bit differently. The cool down period may be a little bit different. If they quench it, like on an tempered iron core, in a salt bath or something like that, those are all definitely little things, but it's never going to be a perfect line through there. And I think that's what most people just assume, that if, when it's heat treated, it means it's ground heat treated to a certain depth or all the way through, which in this case on a cast cam core is not true. But you can see where they can run into those issues. You get into the edges here, and if you're not careful with how you grind that camshaft, you could get into the heat treat fairly quickly. If you get into the heat treat and you grind that cam very low or in an area where it's going to wear down, you could get into this softer material. Everything in the gray here is a softer part of that camshaft, and it's what we just snapped apart there on that other cam. Everything here in the shiny part, because it's been a little bit polished to get it to enhance that, shows you the depth of the heat treat. So it was very important for me to do that. I wanted you to see just exactly what they look like. Now we can look at the ends of the camshaft here, and you can see how much different that looks like on the barrel side, and what it looks like and how that heat treating goes through there, because you're taking a slice out of that lobe, and so it's going to look a little bit different than the side cut view of it, where you're looking at a full side of the lobe and the barrel to see where it's at. That one is very much on the end. If you look at this one here, it's a different material, obviously, but here's a good example of one where you've got good heat treating. This is a billet camshaft core. You've got good heat treating around the edges, but you got this one edge over here that is dangerously close to being into the softer material and could cause an issue. Now that's a hydraulic roller or solid roller lifter lobe. You can tell by the profile of it. If you look at the lobe on a hydraulic camshaft, it comes more to a flat tappet camshaft comes more to a point. The roller is able to hold open the duration a little bit differently, and the wheel needs to roll on there a little bit differently. But certainly the heat treating is certainly very critical on a billet cam core as well too. But you can run into that situation as well with heat treating, where as long as it's on the side of the ramp side, where it is on the opening side of it and not on the closing, all of the pressure is over the nose on those camshafts or on the ramp here. It's very light on this side, so the chances of that wearing through are thin, but that's a little too thin for my comfort, and I would imagine that camshaft wouldn't pass a quality control test just because the hardness is a little suspect. Now let's take a look at this on what a billet cam core looks like. And again, as we just saw in that example, they are a little bit different. The heat treating depth isn't near as aggressive as it is on a cast cam core, but it's fairly the same. If you look at this one here, that's just a cut of the lobe. You can tell again where the heat treating is on it. I'll get some close-ups of that because it's kind of hard to see it. This one's a nice one. It was just one that was cut down the journal, so you can see how deep the heat treating is on the journal, and everything in that softer, grayer, darker color is the softer part of the cam. Anything that's in the polished side of it is certainly what got heat treated, and that is the depth of the heat treat on that. Let's take a look at that. One is on a billet core that's been cut apart. Now that's, again, it's a hydraulic roller camshaft, and we did the exact same thing. We had this cut down so we could take a look at the inside of it and take a look at the heat treating depth. Now it looks pretty similar, really, if you look at it over the nose here. It's fairly deep in it, and that's where you want it, because again, that's where a lot of pressure, it's where all the spring pressure is on those the cam lobes. You need a lot of heat treating there. It's when you run into those where it doesn't have a lot of heat treating depth in it. But It's just a really good example of what that looks like. And this was important for me to do this because I think the problem with most folks that talk about things like this is they're making an assumption, they're giving an opinion, and I wanted to show you what it actually looked like so you would know when you have those conversations or you're discussing with friends or buddies or reading it on the internet when they talk about that it's a camshaft is at a 50 on the Rockwell C scale. You'll know what they're talking about. It's the hardness of that heat treating, and that's the depth of it. Very, very critical. Interesting thing too on these cam cores, typically on a cast cam core and a billet cam core, they're typically about the same. They both have about a 50 is a pretty acceptable Rockwell hardness number for both of those. So you get into tool steel and some of the other ones, it's a little bit different, but 50 is generally pretty decent on either one of those cams. But again, I just wanted to show you, you look at on the lobe side of it where we cut it apart here. Just very, very important to understand, what that looks like and what we're talking about when we talk about heat treating of a camshaft and what it looks like. Now let's talk a little bit how we can do this at home and test it. Now, this becomes a little bit more complicated because the way we want to look at this and test it, you have to be a little bit careful because you're going to be scratching the material and the surface of it. So you'll need to do it on a lobe or a journal, and that becomes a little bit more complicated. You can certainly do it on the ends of the camshaft, certainly on the back side. I think both of these are this front. Yeah. Dowel pin goes in there, so we know the timing set goes on there. Dowel pin, again, remember, is what indexes how this camshaft is ground. But this little hardness test is nice because it's fairly inexpensive, and you've probably seen YouTube videos on these. They're very inexpensive. I think I bought this set, I don't know, maybe 5-10 years ago, 6 years ago, something like that, and it was $50 or something like that. But the nice thing about this is it's going to give you a bit of a range of where the hardness is on that. Now, one little thing to be careful of here, if you get a camshaft that failed, like this one here did, we had cut apart, you have to be careful because hardening and that process is adding heat. When a camshaft fails, you are adding heat to it again. And what that does is it anneals the metal and it changes the properties of it. So you have to be very careful with it. Really, the best thing to do is to take a camshaft that hasn't been run and that way test it. That way you can kind of take a look at it and see what the hardness is on it. But again, if you do it on one here that's been heated up again and kind of cooled down differently depending on what happened in the engine, you could get some mixed results. So just be careful when you're doing this and understand it. And really the only way to get a good accurate reading on this is to take it to somebody that has an actual Rockwell hardness tester that can take the diamond and do the initial impression in it, and then the secondary one to get an actual range of what the actual hardness is on these things. Again, it's a very expensive piece of equipment. Don't have it here in my shop, obviously, and I wouldn't expect you to either. But again, we'll go back to the tool here. So this is a range. Again, there's a bunch of videos on this that I won't go in too depth in, but it's an HRC scale of 65, and it goes down to an HRC scale of 40. So the best way to do this is to start out with the hardest one, which is the 65. Let's just do it on this billet cam core. I'm going to take a journal here, and let me wipe that off so we can take a look at it. So I'm going to do this, and what I'm going to do is take this file, which is essentially that is, and if you rub it across there with a fairly decent amount of pressure, and it makes a mark, that means the file is harder than the material. When you get to the point where the file doesn't make a scratch on there, it means that the material is harder than the file. Makes sense? So this is a 65. I imagine we're going to make a nice little scratch here. And we do. You can hear it. Kind of see that. So we know that it is not a 65. What most folks will tell you is just keep going down one by one. The next is a 60. The next is a 55. The next is a 50. And just for giggles, let's try the 50 to see how that marks. Ooh, it doesn't make a lot of mark there. Matter of fact, it doesn't at all. So we know that it's at least between a 50 and a 65. Now I'm just going to jump up to the 55 here, see what happens. Pretty strong. It's not making a mark on the 55 either, which means this was a fairly decently hardened. Now let's try the 60. Now imagine this one's going to make a, yep, can hear it digging in. So we look at these, and I'll try to get some close up to this. If you look at these, 65 and then the 60. So we know that this camshaft on that journal is between a 50 and a 55, which for that material, very acceptable. This camshaft, before it was cut into 100 pieces here and destroyed, actually had good hardness on the journals. Now you can do the exact same thing on the lobes, same thing. Yeah, about the same, just catching just a little bit. Let's try the 50. Yeah, it's kind of not leaving a mark at all. So that camshaft throughout is between a Rockwell HRC between 50 and 55. Again, we know the hardness on this camshaft. Now this was a cam that I had laying around. Specs on it weren't any good, and you know, it had never been run before. It was junk anyway, so I don't feel bad about destroying it. But again, you're going to need to make those marks on it. Now, certainly you can do that on the ends of it. It's a lot less intrusive there because you got the timing set that'll go over that, and it wouldn't be a bad place to do it. But just give you a general idea of the Rockwell hardness of that and what that 5150 material was. Between a 50 and a 55, it would be a pass. Now that the billet one's done, let's set that aside and let's take a look at this poor camshaft that we destroyed. Oh, you can see where it hit on the on the floor. That wasn't nice. We'll do the same thing. We'll do one on the journal. We'll do one on a lobe. So again, let's just start with the 50 because generally, if they're going to be in that range of their where it's, I think it's going to be at around a 50, then we should be pretty close here. So this is the HRC 50. Yeah, there's no visible mark on there. So we know it's at least a 50. Now let's get to the 55 and let's see if it made a mark. Can't even really tell where that was. Okay, 55. Yeah, it's starting to make a mark on it. So again, this camshaft, before I dropped it on the floor, before the UPS driver destroyed it, is between a 50 and a 55. Again, this camshaft, without getting too in depth and polishing it so we can see what the barrel or a journal or a lobe look like, we know that the hardness on this camshaft is pretty good. Let's try it on a lobe and see where we're at. Do it right here on the nose of this one, and where are we starting? 50. Yeah, it's not leaving a mark. It's just barely scratching it. So I'm going to say that's a pass. Let's go down to the 45, just for giggles. Oh yeah, there's no way. Yeah, so 45 is no. So let's try the 55, and we'll see what it looks like. Yeah, the 55 is starting to make a mark. So again, I think that's pretty accurate to say that the hardness on that camshaft is a range between HRC 50 and 55. So that's what that test looks like. If you're ever curious about it, again, those are fairly inexpensive. I'll leave a link to it down in the description, so if you want to take a look at it. But again, it's a very inexpensive way to verify on your own what the hardness was. Now, I guess one last thing, because this is a camshaft that failed, let's just try it on this lobe that rolled over and see where it's at there. Let's do the same thing we did. Let's start at a 50 and see what this is clearly down into that area where we could run into some problems. But look how deep that heat treating is over the nose, and I don't think we got that far. So let's try it anyway and see. This is a 50. still about the same. It's not really grinding off any material. Let's take a look at another lobe here. Yeah, it's just skating past it. Let's try the 55 and do the same thing. Yeah. Yeah, a little bit. But again, remember what I said about a minute ago about this being changed, where the heat that caused when the lifter failed and stopped rotating, or the spring pressure was too great, whatever the case was that killed this camshaft, and given by the look at it, I'm going to say it was fairly quickly during break-in or the first couple 100 miles. It's really hard to say, but that parkerizing isn't really worn off there, so I'm going to guess that's what happened, is late break-in, between that 300 and 400 miles initial break-in. But again, because this was heated again by that lifter causes heat. It could have changed the hardness on that, and maybe it was a little false. But again, when we look at the depth of the thing, I think it was fairly evident that the camshaft was heat treated the way it needed to be. It was the lifter that failed on this one. Again, I know this is a sensitive topic, especially if you've had a flat tappet cam go loose. And, we talked about all those reasons for failure in the first video and what things you can do to help prevent that. And certainly the new DLC-coated lifter by Comp, I think, is going to solve quite a bit of that. I don't know if we're going to be able to get to an engine this year to test that. The engine that's in the GMC truck is a hydraulic roller. It was before those lifters came out, so I don't know. But anyway, it was important for me to show this to you. I wanted you to see it, and that way when you hear about people talking about heat treating and depth and all that, and you see something that somebody says that's not accurate, point them right back to this video. Have them watch it. They can see all these little pieces that you've learned and seen, and what that depth actually looks like on the different types of material, and what Rockwell hardness is, and how the process is of how these are heat treated and go together, and a very, very general understanding of how it all goes together, and what the camshaft may or may not do on the failure side of it. So again, I encourage you to keep your eye out for the video from Billy. Again, that should be here just a very short period of time, maybe a couple of months or a month down the road here. We'll certainly ask him any of those questions that you leave down below about camshafts, lobe profiles, how to make horsepower, flat tappet type stuff. And certainly, again, it's a topic that is emotional, so please keep your comments respectful for others. Don't bash a lot of people, with it, or if you had a cam failure, please don't drop a bunch of four-letter words down there. YouTube hates it, and I'm trying to keep this as family-friendly as possible, for as much as I can anyway. So I appreciate it. If you have any questions on this one, don't hesitate, leave them down below. I'd love to answer it. I will leave some more pictures of all this stuff on my Facebook group so you can see any more images of this close up. And again, it's a really, really interesting topic, and I'm glad we had the opportunity to do this before we got to talk to Billy. There will be a third video in this series, and we're going to talk about lifter crown. Again, it's another one that's a little bit misunderstood, so that's what we'll cover in the third video. Anyway, that's it. I hope you guys got something out of it. If you did, leave me a thumbs up. I always appreciate that, and guess we'll catch you on the next one. We'll see you.